So friends, we are in the lecture on risk conscious operation management of complex engineering system, and this is week 3, and the lecture 3 is on deterministic approach to operations. So I am Professor Prabhakar V. Vardhe, and another 25 minutes we will be discussing a very important component of risk-based engineering, that is deterministic approach to in the context of operations. So, okay, the deterministic approach, what do we mean by deterministic approach? Deterministic approach is providing adequate provisions in terms of protection, in terms of redundancy, in terms of diversity, in terms of design, various safety factors, provisions such that we are confident or we have determined that the unlikely event or undesirable event, especially the design basis of the plant, is satisfied. Okay. So, and this approach is the oldest approach, so somewhere 50s or 60s. Its origin is defense environment, and from there it came. So, defense in depth, and then conservative criteria. So, I will discuss those things over here. And let us say, especially for nuclear engineering, it has done wonders, and it was done for other systems also, because nuclear industry has been able to maintain on the highest record of safety. At the back of it, in the background, it was a deterministic approach. Even now, this approach is considered as proven method. Okay. Why? Because lot of gain in terms of risk and at the same time deliverables have been realized through this approach. Okay. But in relatively recent times, the probabilistic approach also came into existence, and now it is considered matured, and this maturity has led to use of this approach, which is not replacing the deterministic approach, but it is complementing or supporting the deterministic approach and making the whole risk assessment more holistic, more reliable, because the certain weakness of deterministic approach are being addressed through probabilistic approach. Certain weakness of probabilistic approach are being handled by deterministic approach. So, this together provides a very holistic mechanism in as part of. And now, since we are developing the applications, so first is regulatory appraisal. That itself is one of the major application in the operational ecosystem. So, risk informed approach is extensively being used in regulatory ecosystem in support of decision making for various cases that are submitted to the regulatory bodies. And now the net effect is regulatory bodies world over, they are encouraging use of probabilistic risk assessment as far as possible and maximize it rather, so that the holistic assessment is possible. And deterministic approach in last 40-50 years have also advanced into best estimate approach. So, we will touch upon that issue also, but core discussion will be on the fundamental feature of risk-based deterministic approach as part of risk-based engineering. So, defensive depth, there are two major considerations. The first major consideration is multiple level of barrier. If and why these barriers? These barriers are required to keep the hazard into the confinements in safe conditions, confined safe conditions. Even if one barrier breaks, there is a second barrier breaks, third barrier, third, fourth, fifth. We will see how many barriers are built, so that the public who are staying around the plant are they are not put to risk. So, and then multiple level of protection. So, multiple level of protection means it is like having multiple systems that doesn't allow the situation itself to propagate actually. That also we will discuss in detail. So, multiple level of barrier and multiple level of protection that exist, and this is called defense in depth, and various elements which support these things. So, first is conservative design, conservative approach to safety. Since this approach evolved since ages, conservatism was built into or it was inherent part of this approach, and this has shown results. Let us say now, if you are getting nuclear power plant extensions, they were designed for 30 to 40 years initially, now they are being extended to 60 years, and again for some now in advanced countries there are scenarios when they are being extended for 60 to 80 years also. How it has come about? Because there was additional margin that was available into the system, built into the system. And the second the thing is redundancy. Adequate redundancy have always ensured, because single component failure should not result into consequences, untoward consequences. So, redundancy, and that, as if that was not sufficient, diversity also is forms part of the defense in depth or deterministic approach core principles. What is diversity? One safety function which is being carried out by a certain system, there will be one additional system wherein the principle of operation right from the scientific fundamentals will be different. Let us say if I am operating a pump, it is by electric motor. Now, what is diversified option? It is turbine, that is power water, which is stored at higher elevation and which takes care of cooling, which takes care of operating the turbine, which is operating the pump in turn, cooling pump. So, we will see this example. So, diversity. If I have to actuate shutdown of the plant, then I have some insertion in rods, they are called safety rods, and the clutch gets de-energized and they enter into the core, plant is shut down. The another principle will be remove the moderator from the core, which was the basic reason for sustaining the chain reaction. Okay. So, these two together, they are operating on different principle. In one case, we have to open a valve so that all the moderator gets dumped, and in the another case, we have to de-energize the clutch so that all our safety rods are inside the reactor. Now, fail-safe criteria. Fail-safe criteria means any design should be such that if the system fails, it should go to the safe state. Like power failure. Power failure should take all my limit switch, relays, boards in a condition they will actuate the shutdown system. So, this becomes a failure criteria, implementation of failure criteria. That means a relay de-energized will de-energize the clutch also, which will insert the safety devices. Then single failure criteria. Single failure criteria means single failure should not affect adversely plant safety. Okay. And then for implementation or monitoring or surveillance program, quality control and quality assurance. Unless until the quality component goes into the system build, quality operation, quality manpower, it is of paramount importance to ensure safety, quality control and quality assurance. In service inspection, passive structures, they need to be then qualified periodically, and that happens by sampling methods. So, and basically they are non-destructive. So, like if you have to inspect the health of a pipe, just go and put your detector or sensor there, and based on the signal that you are getting, tell whether the structure is having any defect or flaws or not. Thank you. So, I was talking about defense. We are using a very short defense in depth, DID. We are using this term. So, how this DID safety management framework is there? Let us see. First, we have hazard, that is fuel, which is sitting in the in a controlled, confined cladding. Okay, so which is okay. So first barrier is fuel. Fuel itself is designed in a manner that the fuel matrix doesn't allow the hazardous product to go out. So that becomes the first barrier, B1. Second barrier will be B2, cladding. That means the tube which is placed around the fuel. And then third barrier will be the coolant system pressure boundary. That is this fuel requires cooling when it is producing power. So the coolant boundary itself provide one barrier. And if this also gives then there is a containment as a fourth barrier. So you can see there are four barriers back to back. The hazard has to cross one level, one barrier, second barrier, third barrier, fourth barrier, and that's how the deterministically we are, though we are not referring, but we are saying chances of fuel going beyond the plant boundary is negligible. We can say when there are four barriers, then similarly the level of protection. Now given a control room scenario, plant is operating, and how the level 1 is implemented, how level 2, that is avoid the control of abnormal condition. First is prevent deviation of the deviation to abnormal condition, then control of abnormal situation, and then control of accidents in design basis. Design basis means the plant is built and its a design basis is made, and accordingly provision exists for safety systems, safety requirements, and that is called the design basis accident. So how we are controlling the design basis accident propagating into beyond design basis, or so if it goes to the beyond design basis, then accident management program and confinement, and then last is offsite emergency response. So these are the protection, the barrier and level of protection are ensured that together make the likelihood of undesired event and especially protecting public property environment. So now how they are basically implemented. So we will see here, these are symbolic, one figure for only illustration purpose has been made. This indicate the containment, and because the objective is to show what are different barriers and what are level of protection. So here on this slide we will see physical barriers. So this is our blue color, we are seeing the fuel which is there, potential source of hazard, and the fuel matrix itself is capable of retaining the good fraction of radioactive product or hazardous product, and then there is a cladding. Even if it is giving away, leaching out, then there is a cladding which is there, the second barrier. Okay, if it leaches out further, we have the coolant system pressure boundary. Okay, I have made the simplified diagram. I am not showing the coolant circulation and things like that, because objective was to demonstrate the barrier logic and its physical this thing effect. So now, and then even if it comes into the containment, this activity which was confined here just comes into the containment after crossing the clad, and the second, the third barrier, that is coolant boundary, then it comes to the containment. So fourth is the reactor containment. It is a containment which can be isolated during accident condition, and it is ensured that the public is kept safe. There are no radiation consequences outside the plant boundary. And then these are the and then the last barrier is the exclusion zone. It is a fifth actually barrier. almost like more than 1 kilometer, or maybe 1.6 kilometer, and these are called exclusion zones. Here public habitat or public entry is not available. So in this area beyond this boundary, public resides, and in this area only employees and professionals will be living, and that's how this itself becomes exclusion zone. This itself becomes one of the barrier for radiation consequences. Okay. So this is all we were talking about a reactors example. So 5 barriers that we have discussed here. Now let us see how we implement the protection level. Or before that we will discuss, because this will come again and again. Let us say we talk about redundancy. So let us say this is symbolic of a reactor, and then we are monitoring certain parameter. Okay. Actually speaking, normally systems have one sensor only, but in safety critical system or complex engineering system like nuclear plant and other systems, there is a provision of redundancy. Redundancy means instead of one sensor, there will be 3 sensors will be installed, and this sensor will be operating on 2 out of 3 logic. Even one sensor failure will not affect the system operation. Okay. When 2 sensors fail, then only logic will be activated. When they are deviating for the normal course and all that, they are not, there is a mismatch and all that, then plant will be, safety action will be initiated. So we required 1 sensor, we have provided 3, because it is called system resilience, or having embedded capability in terms of safety. So for example, if you want to carry out a maintenance, it works for reliability also. I can take out 1 channel for short duration and perform maintenance on this channel, and other 2 channels the plant is operating, and this is a regular practice in the plant. Even technical plant safety document, that is technical document, allows for only certain duration you can take it out and put it back in the service. Okay. Now this is an example we are for redundancy that we discussed. Now how we demonstrate diversity principle for safety? Simple. There is a cooling pump here. This pump is operated by electric motor and hydraulic turbine. They are on the same shaft, connected through a coupling. The coupling plays its role when the motor is operating, otherwise they are detached actually. Okay. Now electric power supply is one mode of operation of this pump. Okay. Electricity is there, pump can be operated. The second mode, but if electricity is not there, then what? The pump will not operate. But then when we implement diversity, we provided altogether different, not that another pump will be there as part of redundancy, but as part of diversity there will be power water. That is, there is a overhead tank, power water will come to the turbine, operate the turbine, it will go to underground tank. I have not given the feedback loop just to keep it simple, and then turbine will operate for a mission. Even if we take this inventory as a coping time, then it will the hydraulic turbine will operate. And so here turbine is turbine will be ensuring the operation of the pump, and if motor is not available, vice versa also. If turbine is not available, then electric motor also can. But then we have redundant system, turbine and motor operating on diversified principle. One is by power water, which is for which you don't require any electricity. It is water will enter and operate this thing. For long term scenario, we have to work out certain. So we will not go into that now, but those provisions also exist. But like simply this motor was not available, or so we can pump out this water, or we can use alternate reservoir from here to add to the time. So from this slide, we are able to see how redundancy and diversity are implemented into the plant. Okay. Now multiple level of protection. You know that the figure I have made just for illustration. It is just trying to say that in plant, control room is central to the operation, and humans, they are managing, and there are control rooms have many windows which when any trip or alarms or some parameter goes beyond its limits, then they are indicated, and then like here some alarms are glowing actually, otherwise. So that is one part. Second part is there are hardware or matrix which is shown here, and operator will get the status of the plant after seeing this, like here pump, suction valve, dissolve valve, tank is there, and here some recorders will be there. So we will know the status of the plant by one trip and alarm, this thing which is there visual, and they have visual and audio indication. They will draw the attention of the operator. Then we have some mimic diagrams, panels, and then we have some more mimic panels and some components being monitored. And here what we have is some recorders, monitors, they are placed, and this is symbolic of a console from where the human or operator will maneuver the plant. Okay. So what we say, the first level of protection is prevention of deviation from normal operation. So if any deviation is there from the normal condition, it will be reflected through this main machine interface or control room of a plant. Okay. So any first objective is prevention of deviation. This is first level. So for that what we do is 24/7 surveillance, then automatic actuation of the system. Every time, like for safety actions, operator intervention is not required. Automatic actions are needed. Let's say power failure has occurred. So automatically the on-site DC generator set will start. They will not require any special human intervention, and they will operate, and plant will be shut down, and then in the cooling system required in shutdown mode they will be operating, and operator's role essentially remains supervisor unless until some deviation has occurred, and he is there to control those deviation based on these signals and the information that is coming to him. So automatic system actuations are there, and then human action in some case when there is a deviation, it comes into action, and preemptive corrective action, so that now we are able to bring the plant under normal conditions or safe condition. But it is quite possible that we are not able to control the deviation, then control of abnormal plant. So now deviation has occurred. What we do here, or what is the backup system which brings plant from abnormal path to normal path. So those kind of control actions are also actuated, and then the next level is control of accident. If we are not able to, so you see the different level. First is prevention, second is control, third is accident on design basis condition. That means plant is being built to take care of this kind of scenario. But if suppose by chance, if we are not able to control here, then accident management plan is executed, and there is a offsite emergency. As I said, offsite emergency means the 1.6 kilometer or 1 kilometer, that boundary of the plant, that defines the offsite and onsite scenario. So this is a different level of multi, and this is all part of defense in depth approach that we have in place. Now deterministic approach have evolved into a best estimate approach. The background is like this: the probabilistic knowledge or statistics is one of the enabler for going for deterministic best estimate approach. Second thing is, now we have the proven computer codes, thermal hydraulics is better understood. All this, we have a lot of data on thermal hydraulics, on materials. So this situation is brought in best estimate approach, wherein uncertainty is integral part of it. So this, that we can say the deterministic state of the art in deterministic has moved to the best estimate approach, where uncertainty evaluation is at the core of it. So first is a traditional scenario. What it was there, we used to have factor of safety, because data and models were not available in those days. and that's why conservative approach was used. But now the scene is data is available, computer codes are available, a lot of experimental facilities are available, especially if we talk about the thermal hydraulics. Then this best estimate approach, wherein uncertainty characterization also form part of it, and then regulators will have their own probabilistic consideration. And if you have to sum up this discussion, probabilistic and deterministic, they are combining together and they are trying to give the best estimate approach. And what are the sources of uncertainty? Sources of uncertainties are model uncertainty, data uncertainty, representation, how we represent our model, that is one of the limitation, and that has to do with lot of knowledge, experiment, data. Scaling uncertainty, if we are going from one scale to another scale of the model, let us say there is a 220 megawatt plant. Now I want to have the similar study for the 440 megawatt plant, or so scaling is required. So scaling may not be linear always. So that uncertainty are always there. Boundary and initial condition, they pose huge uncertainty, and user uncertainty, how people will be using that end effect, that whatever changes we have done. And totally all they are form part of sources of uncertainty. Okay. So how exactly it goes is from one of the IAEA guide, because I thought this is the right way to touch the subject. There is a IAEA guidance to handle uncertainty, and this is a document which has been developed, and I have given the code. It is available in open domain, and you see from probabilistic domain, this approach is a normal distribution, upper bound, lower bound have been given, and of the parameter, and those things, uncertainties are formulated here. Best estimate computer codes are developed, and then relevant experiments are done. Now, and then we have best estimate value of uncertainty here. So this was a symbolic thing. So we can see here the thermal hydraulics, which is essentially deterministic component, and probabilistic uncertainty estimation, they join together to give the best estimate, and that is the objective of risk-based engineering. Because even if I am doing, for example, I am running a code where all the parameters, they are a point value. So it is in the deterministic domain. But when I do a Monte Carlo simulation, and if I give upper bound and lower bound, which is more realistic of each parameter, so that will become probabilistic code. So result will be also be probabilistic. So they are not basically different component. In fact, they are inseparable component, ideally speaking. So that's how in risk-based engineering we have evolved into this. And then overview of this lecture is defense in depth, deterministic approach, where defense in depth is at the core, barriers of protection, redundancy, diversity, through some illustration also we have understood, and sources of uncertainty we have discussed. Best estimate approach, it is very common now in deterministic analysis. And then we have next lecture on probabilistic, because deterministic, why we discuss, it form part of risk-based engineering. Now next is probabilistic approach.